Select the graph of the polynomial function. Note the intercepts, multiplicity, and end behavior. So to begin with, let's start off looking at the intercepts. So for instance, we have our polynomial in factored form, so it's going to be easy to identify the zeros. And the zeros, as long as they are real numbers, are x-intercepts. So I have a 0 at 0 itself, because the factor x, when I set that to 0, I get 0. Next, the factor x plus 1, when I set that to 0 and solve, I have a 0 at -1, and then also at +1. So I can go ahead and eliminate any graphs here that don't have 3 zeros. So for instance, this graph only has zeros at 2 places, so therefore it can't be the graph that we're looking for. And the rest of these have zeros at 3 places, so we will look at other aspects. Now, the multiplicity of these zeros. They're all multiplicity 1 because there's no exponents of 2 or higher on any of the factors. So they're all multiplicity 1, so the graph crosses through the axis of these particular places. Then the last thing that we can look at is end behavior. So this is a polynomial function with 3 zeros, so it's degree 3. And the most basic degree 3 polynomial is x cubed. And its graph looks like this. But since we have a negative coefficient, that negative coefficient, what it does, the 2 stretches the graph out, but the negative inverts the graph. So our actual graph is going to look more like something of this nature. Doesn't really tell us what's happening locally around the origin, but it does tell us as we go to infinity that we should be positive on the left-hand side of the graph, negative on the right-hand side. So the end behavior then doesn't match up with this first graph, so we can eliminate that possibility. And it doesn't match up with the third one either, so we can eliminate that possibility. But this graph here, this third one, is perfect. It matches up with all our requirements because it has zeros at -1, 0, and 1. All of those zeros we cross right through the axis and the end behavior matches up.